All right, go ahead, Camille.
So we have an invited guest, Berk Ustun, who is with us today to give a talk on the work that he's doing with artificial intelligence. He's an assistant professor in the Jacobs School of Engineering, affiliated with the Computer Science and Engineering Department, but also with our Data Science Institute. And Berk's also a co-investigator with me on the ethics core for Bridge to AI. And he gave a talk to our core about probably 6 or 7 months ago that was just really informative. And so I asked him if he would share that talk with us, or a version of that talk with us today. So he's here to give to share the work that he's doing, and to also we'll have time for Q&A at the end. So Berk, I'm going to go ahead and hand it over to you, and you can fill in any gaps of your introduction that I didn't hit on, because you know a whole lot more about what you do than I do.
Sure. Yeah. Thank you, Camille, for that introduction. Yeah. So as Camille said, I'm an assistant professor of data science and computer science at UCSB, and I'm primarily, or my research is primarily focused on machine learning, and specifically on topics like algorithmic fairness and on interpretability. So let me just see if I can share my screen to get things started. Right. So yeah, the talk that I'm going to give today is primarily going to be about personalization in machine learning. So it's going to be a large talk that touches on fairness, on privacy, and on consent. And it's primarily focused on healthcare applications. So I'm actually really thrilled to be able to present to you all today. I think that there is a lot of room for work in this area, and I think that it's hopefully going to be relevant to some of the problems that you're working on, and that there might be some takeaways that could lead to a big impact on some of the problems that you guys are working on at AI Ready. So yeah, let me get started. So I guess my starting point for talk today is really fairness in machine learning. So I know that a lot of you are familiar with this topic, but for those of you who aren't, I'm sure that you've seen kind of articles like this, right? So big company uses machine learning to automate an important decision, say lending or hiring. They build a model, deploy it, and a few clicks later, they get into trouble because it seems to predict or perform differently at a group level, right? So these are kind of the stories that motivated a lot of the work in algorithmic fairness and in fair machine learning. And I guess the idea is, in lending and in hiring, we have laws in place that say we should make the same decision based on protected characteristics like age, sex, race. And so if we're going to use models to inform those decisions, well, they should predict and perform in the same way across these groups, right? And so this is an important goal, and there's been a lot of work on it over the last few years, since about 2015. But I think, at a high level, it doesn't cover a host of applications where we would care about fairness. Okay? So just as an application, in medicine, for example, we also work with models that make important decisions, and we also care about how they affect specific groups, but we don't build models that predict or necessarily perform in the same way across groups, right? So here, for example, is the Chatsu Bath score. This is a scoring system that's used to predict stroke risk, and you'll notice that this model uses variables like age and sex, right? And that means it doesn't assign the same predictions across protected groups. And in this case, it's actually a good thing, right? Because the risk of stroke can change dramatically based on your age and sex. And by accounting for these variables, the model is able to target those differences and hopefully assign more accurate predictions of stroke risk, right? So what I want to get to here is that somehow in medicine, the rules of the game are different, right? And the reason for this is really because the ethical principles are somewhat different. In medicine, your ethical principles are things like beneficence and non-maleficence, right? So do the best and do no harm. And what that means from a modeling perspective is that you should build a model that maximizes performance for every group, without harming any group. So the practical way to do this is really through personalization, right? As a practitioner, you have this large database that contains all sorts of information, as well as features like age and sex. And you know that stroke risk might vary based off these characteristics. So obviously, you're going to go ahead and fit a model that uses the information so they can target these groups. And by doing this, your model has the flexibility to target groups and to assign more accurate predictions to each group. And somehow this flexibility is optional, right? So by including these variables, you aren't necessarily harming any group. So in some sense, the view is that by doing this, by personalization, you can only really make things better. So this is kind of idea really leads, I think, practitioners to personalized models that use all kinds of personal information, right? So just as another example, here's the Denver HIV risk score. This is also a model that uses age and gender, but you'll notice that this also uses things like race and ethnicity and sexual practices, right? And now you're starting to use kind of information that might be sensitive or that's self-reported. And the point I want to make here is that really all of this really hinges on the belief that a model that accounts for these characteristics can only be more accurate. Okay. But to be honest with you, like no one actually knows that this is really the case, and that's because no one checked. So here I want to show you maybe how things actually work at a group level. Okay. So here I have I'm going to show you an example from a real world data set. This is a small data set where the goal is to predict obstructive sleep apnea. And I have two group attributes, age and sex. And so I'm going to use that to build a classification model that predicts whether patients have obstructive sleep apnea. And in this case, I'm fitting a logistic regression model with a one-hot encoding of these group attributes. And that model is personalized. So to see if personalization actually makes them better, I'm going to fit another model without the group attributes. So this is logistic regression without the one-hot encoding of age and sex. And in this case, I see overall improvement of 1%. Right? And so this is in training error, but the model generalizes, and this type of gain holds on test error as well. But this is overall improvement, right? So let's go ahead and see how this holds across groups. Okay. So now when you start looking at the gains across groups, you'll see that the gains are not even, right? They're not the same across groups. Some groups really gain from accounting for age and sex. Some groups maybe gain a little bit, but some are actually worse off, right? And in this case, I would argue that this is harm, right? And the reason why is because, well, these people are providing personal characteristics under the expectation that they're going to receive better, more targeted predictions. But what they're getting is really quite the opposite, right? They're getting less accurate predictions. And this effect is unintentional and it's entirely avoidable, right? So in this case, for example, for these groups that are actually performing worse, you could have just done better by using a model that didn't include age or sex in the first place. So my talk today is really broadly going to be focused on its effects. And what I want to do is really formalize it through a concept that's called fair use. I want to use that to explain why effects like this happen and how they look like in practice. And then I want to touch a little bit about different approaches that we can use to fix it. One through testing and budgeting for personalization, and another approach that focuses on model development and building models that kind of incentivize people to participate instead of forcing them to report personal characteristics. So I'm just going to jump right in to the first topic. And I'll just start by formalizing some of the concepts that I used on the previous slide. So the next couple of slides are just going to be a little bit of math but it's probably the most math that I'll cover in the entire talk. But it's just a little bit of notation to get everyone on the same page. So I'm going to assume maybe a traditional supervised learning setup. I'll have a data set with features, labels, and group attributes. And in this case, group attributes are categorical attributes like sex or age groups. And I'll be interested in performance in how a model performs across intersectional groups. So females under 60, males over 60, so on and so forth, right? And so what I'm going to do is use the data to train a personalized model that uses age sex, that's HP. And so this, you can think about it as a logistic regression model with dummy variables for sex and age. And I'll assume that the model is trained to minimize empirical risk, so just the error rate. And to make sure that it's working the way it should, I'm going to be evaluating performance at the group level. Right? So I'll be looking at, for example, the test error of this model on females under 60, on males over 60, and for the other two groups. Okay. So with that, I'm ready to present maybe some conditions that could describe what fair personalization could look like. Okay. And maybe this first condition that I'm going to talk about is called rationality. So rationality is a condition that says that when I have a personalized classifier, each group should expect better performance from my personalized model as compared to a generic model that doesn't use group attributes, right? So that's HP is my personalized model, H0 is my generic model that doesn't use my group attributes, right? And so this H0, I call it a generic model. And that's a model that doesn't use your group attributes. And it's meaningful because it's something that you can always produce by just repeating your training process on a data set without the group attributes. Right? So previously, I was training a logistic regression model with dummy variables. Here, I just drop those dummy variables, repeat my process, and that's how I get my generic model. And now the second condition that I want to talk about is called envy freeness. So this is a condition that says that each group should expect better performance from personalized model when it assigns their personalized predictions rather than personalized predictions of any other group. So this is something that you can think of as, say I took my logistic regression model with a one-hot encoding of age and sex, but I reported a different age group or a different sex group. Well, in that case, my performance should decrease. And in some sense, I should expect the best performance by truthfully reporting my actual attributes. Right? So these conditions really reflect basic expectations of groups from personalized model. The first one says that personalization should lead to a gain in every group. The second says that the gain should be tailored to each group. And so these are collective preference guarantees, meaning that they hold over groups, and they really apply in settings where each group performs a model that performs better. So this is something that makes sense in applications like clinical decision support, where it's possible to expect patients for more accurate predictions of disease risk or treatment response. But it's not something that holds in applications like lending or hiring. Because in those settings, groups might perform models that assign a specific prediction rather than the most accurate prediction, right? Just because a specific prediction might be the one that leads to a loan or a job interview. So the reason why we call these fair use conditions is really because they work in a way that's similar to fair use conditions in law. So in law, for example, fair use conditions state when you can use copyrighted material without asking for permission from the copyright owner. Okay? And here, what these conditions are stating is when you can personalize a model with information without asking for permission from the groups who would provide that information. So maybe a nice way to kind of enshrine this is through is really by asking, well, what would happen if we could actually ask for permission from groups to assign personalized prediction? Right? So say, for example, that we let each person either report their group membership, withhold it, or report the group membership of another group. Okay. If a personalized model obeys fair use, then each group really expects to receive the most accurate predictions that they can by reporting their true group membership. Right? And what that means is that the model is really using your personal information in a way that is aligned with the interests of each group, at least an expectation. And so I think about this really as a necessary condition for truthful self-reporting. I suppose that if a model violates fair use, it means that people would not have reported their personal characteristics voluntarily or truthfully. And it's important to say it's necessary, not sufficient, right? So if a model obeys fair use, a person might not report their personal characteristics simply because the gain is insufficient. Right? And so maybe the best way to kind of use these conditions is really as minimal requirements that flag harm rather than kind of a rubber stamp for fairness. Okay, so based off that, I guess, when should we really care about fair use? So I can think of several examples that I touched on in the introduction. Maybe the first is when we're personalizing models with information that might be self-reported. So things like substance use, sexual habits. In a situation like this, if fair use conditions are violated, well, that would mean that anyone who knew that they were getting worse predictions by reporting information would not voluntarily report. Another big use case is really where political prediction models are using protected variables like sex and age. In this case, fair use violations reflect kind of discrimination because you're assigning unnecessarily inaccurate predictions to groups that are defined by immutable characteristics. And then a whole host of other use cases arise when you have variables that are reported at some kind of cost. So that could be variables that are sensitive, where there's a privacy cost or a cost of disclosure that's associated with reporting this information, right? If the information doesn't lead to gain, then why are we asking people to report it in the first place? And another case is, for example, where there's really a tangible cost. So something like a lab test, biopsy, some kind of procedure that's used to obtain additional information to assign a prediction. Okay, so this could be a lab test. It could also be something like psychiatric assessment or a battery of tests where it requires either time, effort, or money. So the last thing I really want to talk about with fair use conditions is why they're actually violated in practice, right? Somehow this result that I showed at the beginning of the presentation is a little counterintuitive, right? But to me, I mean, I guess it actually it isn't as counterintuitive as it looks, primarily because a lot of machine learning methods are designed to train models in ways that optimize performance at an aggregate level rather than across groups, right? And so really the only guarantee that you get when you run a machine learning algorithm is that it's going to use group membership in a way that will improve aggregate loss on training data, right? And so that means that you will get fair use violations if, for example, you're not optimizing properly, or if you're optimizing for a surrogate for your performance metric. So for example, if you really care about prediction error, but you're optimizing the SVM, which is really which is actually optimizing distance and decision boundary. Another issue that and say, for example, you can resolve these issues in training, well, then you might run into issues with generalization. So for example, a model could obey fair use in training, but violated in testing, right? And I think both optimization and overfitting are kind of well-known issues that we know how to deal with in machine learning. But I suppose what really makes them tricky to deal with here is that you have to intervene at a group level, right? So say, for example, that you notice that your model is overfitting and you want to correct this by shrinkage, by regularization. Well, all the methods that we have to do that are really guided by overall error, right? And so if you tune parameters or you shrunk or you add some shrinkage, that would really do things at an overall level. And you could probably fix a violation for one group, but get a violation for a different group. Okay. And so in some sense, in this regime, your performance is coupled. And sometimes that actually occurs by design, right? Because of the specification that you put on the model. And so here's maybe a simple example of this issue of misspecification. And I want to talk about this in a little bit more detail because I think that it's one issue that is very difficult to address. And it's also something that I'll return to at the end of my talk. So here, for example, I just have this simple stylized classification task where there are no features and two group attributes, sex and age. And I have a data set that has 50 positive points and 51 negative points. And my goal is to build a classifier that can use this to predict positive points, right? So in this case, for example, if I train a logistic regression model or any classification model with a one-odd encoding, so dummy variables for the groups, well, in that case, I'm going to make 24 mistakes simply because I can't predict interactions with that type of variable. And then in this case, for example, if I train a generic model, well, that's a model that is just trained with futures. In this case, there are no futures, so it just assigns a baseline prediction of negative to everyone. Right? So in this case, for example, you kind of have this very hallmark example of personalization where you account for group attributes in your personalized model. It leads to an overall gain, cutting the error by half. But you can see that personalization works really well at a population level by targeting these two groups that you weren't targeting well before, but it still leads to harm, right? So in this case, for example, there's a minority group of old females who will get worse predictions as a result of personalization. And then the majority group actually, well, they were the groups that were getting good predictions to begin with generic models. So they're reporting additional data without getting any gain in return, right? And so something like this is really difficult to fix without testing, right? You could maybe fix this by fitting a more complex model. But in general, you really don't have this kind of insight or this kind of flexibility because there's just too many groups. And you'd have to specify a model class that is just flexible enough to be able to target each one of the groups. And then you'd have to fit it in just the right way so that it can actually perform well on each one of the groups that you're dealing with. So with that, I want to move on and just maybe show you what things look like in the real world. So here I'm going to show you kind of results from a case study where we train a logistic regression model that's meant to predict mortality for patients with kidney disease. And in this case, your group attributes are sex and race. And so just a context, because we're using race in this case. So this is kind of a long-standing practice in medicine. And it's really being put under spotlight right now. There's a bunch of papers in New England Journal of Medicine, in Science Advances, that are examining this practice and that are looking at this idea of race correction and whether it's warranted at all. And personally, I think there's a lot of good reasons why you shouldn't use race, but maybe in the context of this talk, one really good reason why you shouldn't use race is because it doesn't actually do what you think it's doing. So here's some evidence of that. Here I'm showing you the change in accuracy that's associated with each fair use condition. So on the left, I'm showing you the changes in accuracy that result from rationality. On the right, it's for NV freeness. So in this case, this rationality gap, it's the gain in accuracy that you get from the generic, between the generic and personalized model. And the NV freeness gap is the gain in accuracy that you get from a personalized model where you report your actual group attributes, and a personalized model where you report group attributes of another group. And in this case, each one of these boxes shows the gains, and it's shaded by the p-value of the hypothesis test. So in this case, red is bad, blue is good, and your null is that personalization is really working as it should. So if you get red, that means that there is enough evidence to suggest that there's a statistically significant instance of personalization. Okay. And so really the main takeaway in this slide is that you see that these conditions, these minimal conditions that you expect personalization, are violated all over the place, right? You see rationality and NV freeness violations in training data, in test data. Some of them can be large, some of them can be small. And in general, we run hundreds of experiments like this in our first paper. And what we find is that this kind of thing arises throughout all sorts of model classes, throughout all different types of model classes, all different types of personalization techniques, and all different types of prediction tasks. So whether you're predicting error or AUC or calibration. Okay. And in general, I think there's really no good way to avoid it from the start. But one thing that you can do is test for these conditions and in model development and make things better through testing and iteration. So for example, here is the rationality gap when I use a logistic regression model with a one-hot encoding. One option that you could have in this case, after seeing fair use violations, is to maybe use a more nuanced approach to personalization. So in this case, I would use an intersectional encoding. That's just dummy variables for the intersectional groups. Alternatively, you could also use a more complex model, or you could also rebalance the sample sizes, right? And you can see that by doing these types of iterations, you can make things better. But sometimes by fixing violations for one group, you end up getting them for another group. And so in general, there's no silver bullet. And interventions can really minimize the occurrence of these violations, but they might not be able to resolve it. So with that, I do want to take a step back and say, look, something like this is a little messy, but I want to point out that it's not necessarily hopeless. Like for me, when I see this, what it means is that it's really hard to actually build a single model that is equally well personalized for all groups. So if you really wanted to have a reliable, kind of surefire way to fix this kind of issue, the easiest way to do it is to really predict using multiple models. Okay. So here I'm showing you the same numbers as before, just to show how you can resolve these types of violations by working with multiple models. So in this case, for example, the most basic thing that you can do is assign prediction to groups who have rationality violations using a generic model. So you use a personalized model when it works, and you use the generic model for groups who don't gain from personalized model, right? And so this is something that will always resolve rationality violations. And then maybe another strategy is, whenever you see a fair use violation for a specific group, well, you take that as a sign that somehow personalization isn't working for that group. And so you spend time to maybe build a model that is specifically personalized for that group. So for example, one thing you can do is train a separate model for that group using only the data for that group, right? And so that's, that's called decoupled training, and you build a decoupled model. And you can see that in this case, you can really achieve high gains for these groups that were suffering from instances of personalization from the get-go. All right. So this really brings me to the next part of my talk, which is maybe about testing, right? So in the past couple of slides, I think the point I really wanted to make is that testing is important because there is no guarantee on fair use, right? If you want to make sure that personalization works, you need to test. If you find out that it doesn't work, you need to test. If and if you want to somehow fix issues, the right way to go about it, at least, is through testing and iteration. But the issue, I think, with testing is that testing is really unreliable just because we work with a fixed number of samples whenever we're developing clinical prediction models. Okay. So, for example, whenever we build a clinical prediction model, we work with a database, and the number of patients in our database is fixed. And each time we build a model and we personalize it with one group attribute, we increase the number of groups. And as we add more and more group attributes, well, we increase the number of groups exponentially and decrease the number of samples per group exponentially as well. And so, at some point, you can really, test all that you want, but it becomes really hard to say if personalization is really working as it could be. So in this case on the right, for example, there are just too many groups. And for all the groups, even you could test fair use, but the outcome that you get from a hypothesis test is not going to be conclusive. Like personalization could be working, it couldn't be working, but you just can't tell. And so the second kind of work that I want to talk about is really to try to characterize this kind of boundary point where we can really tell whether personalization is working or not. And so that's something that we call an epistemic limit. And the idea, I think, is to try to define this epistemic limit so that we can budget for personalization. And in particular, we really want to find a very conservative limit. And so in particular, we want to find a limit where we know how many groups or how many group attributes we can use so that we can always test for fair use without making any assumptions. So to set things up here, I'm going to go ahead and just have 2 more slides of kind of notation. We'll just use a simple kind of hypothesis testing setup, and we're only going to test for rationality. And the metric that I'm going to test for is the thing called the benefit of personalization. So this is really the minimum gain in accuracy that a personalized classifier has across all groups. And this metric itself is really useful because it can let us run a single test that ensures rationality for all groups. Okay. So in this case, our hypotheses look like this. Here, the null hypothesis says that your benefit of personalization is negative, and that means at least one group suffers from fair use violation. And the alternative is that your gain is greater than epsilon, and that means that all groups benefit from personalization by this amount epsilon. And so in this case, our default assumption is that personalization will inflict harm. So we want to reject the null in order to kind of show that personalization is leading to a gain for all groups who are sharing personal information. Okay. So, oh yeah, sorry. And so just to formalize this, I guess the way I think about hypothesis testing is through a decision function that basically takes this personalized classifier, the generic model, a data set, this value epsilon, and it outputs 0 or 1 based on the hypothesis that you end up accepting. And so all this is really used to kind of characterize how we're going to go ahead and identify this epistemic limit. And the idea here is really to identify it in a way where we can create a bound on the reliability of hypothesis testing. So the reliability of hypothesis tests are really defined by the sum of type 1 and type 2 error. So this is going to be, the probability that you say that personalization is working when it doesn't, or where you claim that personalization doesn't work, but it does, right? And in order to kind of avoid making any assumptions on the type of hypothesis test that we're going to use, what we're going to do is come up with a minimax bound on this probability of error. Okay. And so what that is going to say is basically, what is the probability of error? So given my, data set, let's assume that it comes from data distribution, and let's assume that it comes from the worst possible data distribution, right? And say that given this, I picked my hypothesis test to be as reliable as possible under the worst possible data distribution. Okay. So in this case, if I could actually go ahead and design a hypothesis test that somehow minimizes the worst case reliability, what that's doing is that it's giving me the reliability of the safest possible test. And if I choose any other test, what that means is that there is some data distribution that could make it unreliable. So with that, I think the kind of main technical contribution of this work is this lower bound on the probability of error. And it's primarily a technical result, but it really has kind of very meaningful statement associated with it. So specifically, what it really does is that it kind of couples all these quantities to say, given a personalized model and a certain data set and a certain level of gain, how many samples do I need in my data set? How many group attributes can I use so that I can always test reliably for fair use, right? Say, for example, I wanted to test for rationality with a gain of 1%. If I have a data set with 8 billion points, 1 point for each person on Earth, in this case, for example, you can find that any classifier with more than 19 binary attributes has a probability of error, has a worst case probability of error that's greater than 50%. And so there is some data distribution where that test is going to be more unreliable than coin flip. And practically what it means is when you personalize a model with more than 19 possible attributes, well, you can no longer tell that personalization really works for every group. So even if you pick the best possible hypothesis test, right, there is some data distribution that will make your test too unreliable. Okay? And as soon as you start to personalize with more than 19 attributes, somehow you're banking on the fact that your data distribution is not somehow out of the norm. So in general, we can take that bound and kind of repeat it over and over to get what's called a personalization budget. So here I'm showing you what this looks like in practice. And these are really kind of budgets that are derived by applying this bound to different sample sizes and different gains. And on the left, I'm showing you budgets that are expressed in terms of the number of binary group attributes. On the right, it's budgets are expressed in terms of the maximum number of groups that I can target. So say, for example, that you have a data set that has 50,000 samples and you want to ensure that personalization benefits everyone by giving a 1% gain in accuracy over a generic model. Well, in this case, these budgets tell you that you could either have 4 binary variables or you could target 15 groups. Okay? And so again, these are limits that really identify like the safest possible budgets for, or budgets for safe personalization. So if you stick to within these limits, you're bound to be able to test for fair use reliably. If you go outside of them, you could be okay, but there's no guarantee. There's always some data distribution that could lead to unreliable testing, and you wouldn't be able to know. Okay. So, okay, in the last part of my talk, I want to quickly go and just cover how we can go ahead and kind of resolve or ensure fair use through model development, right? So I think one high-level approach based off everything that I've presented so far is testing. Another one is really to train models that obey fair use guarantees in the first place. And I think that second approach that I'm talking about is something that's viable, it's interesting, and it's what I think a lot of people would do in kind of fair machine learning. But I think one fundamental limitation of building models that have built-in fair use guarantees is that really fair use itself is a bit of a low bar, right? It's necessary but not sufficient. If a model violates fair use, it means that individuals would not consent to personalization. But if a model obeys fair use, individuals might not report. Right? So in this last part, I really want to show you maybe another approach that works around participation and tries to incentivize consent. And I suppose the starting point or the motivation for this is really, well, what if we gave everyone the option to report their personal characteristics at prediction time? So let's go ahead and test this idea. So here we have this classification task that I presented earlier with the four groups and the personalized model that leads to fair use violation. In this case, where 30 groups were receiving worse predictions as a result of misspecification. And let's see what happens when we let people go ahead and choose between the personalized model or the generic model. So in this case, for example, old females, well, they were suffering from fair use violation. And so they would gladly opt out of personalization and receive predictions from the generic model. These two other groups would opt into personalization since that leads to the most accurate prediction. And young males, well, they would opt out as well because they could get the same predictions without reporting any information at all. So if there's even, a minimal cost of reporting age or sex, individuals would rather prefer not to report than to report and get the same predictions. And so here you can see by, just by kind of letting people report their own group attributes, you can resolve all two of these fair use violations for each group. And that improves accuracy for each group. And as a result, it also improves accuracy for the population as a whole. And I think, one last effect of this is that you end up collecting less information overall. So in this example, maybe it doesn't really matter because what you're collecting is age and sex. But in fact, this is kind of good thing that you want to have if the information you were collecting were the outcomes of lab tests, right? So in this last line of work, what we want to do is really develop models that work in this way. And what we call them are participatory systems, right? So formally, participatory systems are really prediction models that operationalize this notion of informed consent. So in a participatory system, what you do is you let each end user either opt in or opt out of personalization at prediction time. This is kind of like a self-reported screening tool where individuals have the ability to opt out of providing specific features or answering specific questions. Okay? And in this case, for example, they would do this after seeing the gains of personalization. Okay. And so, you can imagine that there are very different approaches to building these types of systems. And in fact, we have 3 different approaches that all have their different benefits. So I'll just quickly kind of run through this just to give you just the idea. One way, for example, is to build what's called a minimal system. So this is a system that you can build just by building fair use conditions. In this case, you have a generic model that's trained without personal attributes. And each user can either opt out of personalization and receive predictions from the generic model, or opt into personalization and receive predictions from H1, which is their personalized
I mean,
model.
I'm muted. It's just my nice background music.
And then so I suppose, one issue with this
Yeah.
setup is that every user who opts in must report all their attributes. So a different system, for example, is what's called a flat system, where individuals are allowed to report any subset of their attributes. So this is a case where, for example, you can not only report, female old, female young, but also female or old or young. And this is a case where, for example, we don't have necessarily the models to assign those personalized predictions. So what we do is we relax the assumption that we have to either have a generic model or personalized model, and we allow for all sorts of different models that use different sorts of personalized information. And so we get an ensemble of models that's personalized for each possible subgroup. Okay. And then I suppose one issue with this, right? So I mean, I guess like the reason why we really call this a flat system is because when a user comes in, they can see all the options they have for reporting that are laid flat in front of them. And I suppose one issue with this is that it's really not great when you want to have to decide what to report. So here, for example, a user who has to decide what to report has to compare 4 different models. If they had 3 binary attributes, they would have to choose between 8 different models, right? And so this last system that we have is really built to kind of simplify this by putting things hierarchically and building and letting them make sequential decisions. So this, in some sense, simplifies decision making because they can report one attribute at a time. And it's also kind of an architecture that's useful if we're personalizing models using attributes that could be acquired if needed. Right. So, for example, if a person needs an interview or a lab test, that's something that maybe you want to defer to only the groups that could really benefit from it. And that's the case where, for example, a sequential architecture could make sense. So each of the systems ensure consent, but they don't lead to participation. And I suppose that the idea is really to build them in ways that will incentivize participation. And the key point I want to make here is that by letting people opt in or opt out, what we do is we take this prediction model and we turn it into a market for personalization. So in this case, for example, if the model gives negative gains personalization, so fair use violations, people opt out. If there are insufficient gains personalization, people also opt out. And these two things really set into place the right types of incentives and safety nets, right? In some sense, by building this, people are protected from fair use violations because they won't report data that leads to worse predictions. And at the same time, model developers are really incentivized to make personalization work well at group level, right? Because when they do, then people opt in. And every time you opt in, you can assign more accurate predictions to each group. And those gains add up and help you towards your goal, which is hopefully to predict as accurately as possible at a population level. Okay. So I think I'm going to skip over the next slides, which are basically about the way that we would build these systems. But I can talk about that later. But generally, it's described in our paper, and it's kind of a tree induction algorithm that can build these sequential systems by choosing a reporting interface and assigning models. And this is code that we wrote and that we're about to release, but it's very flexible and you can build kind of participatory systems for any classification task with kind of 8 group attributes and any model class that you wanted. So it would allow you to do things like mix up logistic regression models and random forests that are personalized in different ways. And it will layer them in a way that I guess will incentivize personalization and maximize performance at a population level. And one kind of feature here that it has is that not only does it kind of try to maximize the gains that are given to each group from reporting, but when gains aren't possible, then it will just avoid asking individuals to report by pruning those options from the tree. Okay. And then here's the last kind of slide just to show kind of the gains or the effects of building a participatory system in this case. So here I'm showing you systems that were built with random forest for an ICU mortality prediction task. And you can see that, for example, a baseline model in this case leads to a fair use violation. A minimal model can resolve that by not asking for attributes that would lead to harm. A flat model, a flat system could make things even better by not only resolving the fair use violation, but really assigning a personalized model to each specific group. And a sequential model really performs the same way as a flat model, but it gives us additional ability to kind of make more informed decisions one at a time. Okay. So I think just in the last minute, what I'd like to do is just maybe sit and wrap up the talk and talk about the big picture. And I think the big picture is really that, personalization, I think it's this practice that we use a lot in machine learning, and that I think we presume makes everything better in terms of performance. And that's something that's true at a population level, but it's not true for every group who provides personal data. And so this is something that we weren't aware of, but it's also something that I think we can measure, that we can check, and we can fix. And I think the work that I presented today is really focused on highlighting different ways to measure and fix this. So one way to do it is just by evaluation and testing. Another is through budgeting. And a final approach is by building models that have fair use guarantees. And so this, I think, is all very early work, and none of it is really operationalized, but it's a proof of concept to show how things could work. And I think that it's really relevant in clinical prediction tasks with group attributes, but also, for example, other types of models that we're building today. So with that, I think I just like to end there. Leave some time for questions, and just on the last night, I just want to thank some of my collaborators with whom we worked on this work.
Thank you so much, Berk. I see one question from Dr. Baxter in the chat. Sally, do you want to ask it, or should I read it?
Either is fine. I can ask it. Yeah, it's always a very interesting talk. Thank you so much for sharing your work with us. And I know, like, a lot of the examples may just be like sort of simplified to allow better visualization and whatnot, but just curious, like, if you in your work you've looked at the effects on performance or error rate when you also look at interaction terms, right? So sometimes we don't just have age, gender, clinical variable. We may have interaction terms of like gender times smoking or whatever, is being looked at. And so if you were to take out that variable, it would affect not just the sort of one hot encoded variable, but also any interaction terms that the variable might be involved in. So just curious if you've looked at that analysis and what you found, if so.
Yeah. So so this is a great question. So we have looked at that. I mean, I think just by default, we like for the first two projects that I mentioned, I think all the groups that I was talking about were really intersectional groups. So they were always defined by combinations of group attributes. And that's specifically for the reason that you're mentioning, right? If you look at things one group at a time, like you could end up gerrymandering, where things would benefit maybe patients who are old or patients who are female, but not necessarily patients who are old and female. I think that in general, using an intersectional encoding kind of avoids this effect that that you're missing an interaction effect. But we find that it can still lead to fair use violations as because basically, if you include dummy variables, for example, for interactions between group membership, you also have to include interactions between group membership and features. So it has to be kind of like age, sex, and then blood pressure, right? So I think the only way to really avoid that is to train decoupled models or sort of separate models for each one of those interaction terms. And that basically accounts to kind of including all possible interactions. So that actually works really well. The only requirement there is that it just requires a lot of data for group, right?
Yeah.
Yeah. But I mean, kind of one of the takeaways from all this work, I think, is that when you have enough data, there's really nothing that beats a model that's separately trained for each intersectional group.
Okay, great, thank you.
So Sally, I think my question then is, when we think about what Berk's doing and the data set that will be created as part of AI Ready, are there any kind of is there enough, will there be enough data?
I mean, it sounds like that the main thing here is that you be training separate models based on kind of I mean, it seems like there's almost like a combinatorics issue, right? Where you have these different iterations and you train all the different models, but the total number of features doesn't change, right? So I think that it's not as much of an issue of like, if you were to say we need to add, many features in this process, then you would need to see, I think, a corresponding increase in the training data size. And then a lot of challenges we have with like routine clinical care data is there are high levels of missingness, right? Like you have a particular patient where you don't have their blood pressure at the same intervals as, other people, depending on how they interacted with the health system and how many visits they had and things like that. Whereas in this case, if we have like kind of a planned protocol, I think, it's possible we may have people who, if they get fatigued, they may not finish the entire protocol, but in general, we're not going to have that same level of missingness or variation compared to sort of routine clinical care. The broader question is the sample size large enough for the models we're trying to make? That was actually discussed at the in-person consortium meeting, and I think it's still an active area of debate because there are different ways that people approach that in ML in general. But I think this framework of, the different model training and looking at different combinations of features, like group membership and the features, I don't think that will be problematic to try and do with our data set.
Thank you. And Berk, we're at the top of the hour, so I want to be respectful of folks and their time, but just really appreciate you joining us today. Very, very great to hear about your work. And again, congratulations about your paper being accepted. Thank you.
Yeah, no, thank you so much for inviting me.
All right, take care all.